speaker is Surojit Saha. He will speak about core collapse, supernova waveform generation using machine learning.
Hi, everyone. I hope you can hear me fine. Should be fine. OK. So this is Surojit from Institute of Astronomy in National Tsinghua University in Taiwan. And I'm a PhD candidate over there. So if you see that there are 4 dots just next to my PhD candidate, it means that I'm going to defend my PhD thesis in next 4 days. That means I'll travel from here and I'll go back to Taiwan. And on Tuesday, I'm going to defend my PhD thesis. So wish me luck. So you are one of the most lucky people to hear in the first hand the end part of my thesis, even though I'm not going to be talking about a lot in detail. I'll try to put most of the things in a more generalized way. And I've got a couple of very good collaborators with me, Li Ting Ma, Kuo Chen Pan, and Albert Kong, who is also my supervisor. So I've been wondering that till when Marek opened the timetable for the talk, I was wondering where I fit into this. I'm not a model expert. I'm not a detector person. I'm not a electromagnetic person. So where do I fit? Till now, even when I was preparing my slide, I was thinking, where do I fit into this? So please, if I start to speak any gibberish, ask me politely, I'll leave the room. So that's the way. So till now, we had some excellent CCSN talks that covers a wide range of stuff from modeling to neutrino and other stuff. So I'm not going to step on those stuff and express my own. However, I'll put my motivation over here. As most of the modelers know that CCSN simulations are computationally very expensive. You need to spend millions of CPU hours to generate a single wave across a lot of equation of state and other things. So what if we take already simulated waveform and then use machine learning and then see if it is possible to regenerate or reconstruct the CCSN signal across the parameter space? And then if this is successful, we can apply similar method to move forward in parameter estimation. And one of the main goal would be, like in one of the talks of yesterday, if I remember correctly, it was Omicron X. They tried to combine a lot of models for the core collapse supernova, and they tried to detect. So what if we can combine all the existing data that we have for the core collapse supernova, and then we build a hybrid model, and then just enter the equation of state and ask the machine to generate all the required waveforms across all parameter space given for the different models. The most important motivation that I don't put over here is that I like to travel. Since I like to travel, I wanted to come to Warsaw and see everything in person. So that's one of my primary motivation for doing research as well, you can say. So let's talk about the workflow. We, as a machine learning people, we need a lot of data. And on Monday and yesterday also, we had a lot of discussion on the data. And I do agree that for the modelers, it's sometimes very difficult to keep the data into certain format. And then when requested, they might also need to change the format and other things. So as a machine learning people, we really need to have a very clean data before we put everything into the neural network. And then after we have our CCSN data, based on our target, we need to choose the physical parameters. But by physical parameters, I mean on what factors the CCSN simulation has been constructed. And the most important part after that is to build a neural network. If you are familiar with neural network or machine learning, you might know that for specific tasks, we use specific type of neural networks. We don't use a single one for every kind of task. That can be dangerous at times and might lead to overfitting as well as absolutely garbage result. And then we perform some training, test, and validation, which is an integral part of the machine learning aspects. And then For this work, we are going to generate waveforms, the CCSN waveforms, and see whether the machine learning generated CCSN waveforms matches with the true waveforms that are coming from the simulations. And most importantly, after we match them, we also want to verify them qualitatively as well as quantitatively. So for that, I have chosen the data from Righteous et al., and you can find this data available in this Zenodo. And as you might know, that this is a 2D GR hydrodynamic simulation covering only one single progenitor mass and having different equation of state and 98 different rotational profile. So given this data, I choose some of the equation of state as I mentioned over here. And these are the differential rotational parameters that are provided in the given simulated paper. And also the maximum rotation varies between this range. That means for each equation of state, if you put all this together and do some permutation combination with the given profile, for each equation of state, they have 98 different waveforms of the CCSN. And I have all these waveforms from the CCSN across all these equation of state. So here is my data. So I have equation of state, I have A, I have omega, and I have the strain data. So what I do over here is that I take not one exactly, two generative models. One is known as conditional variational autoencoder, and the other is planar normalizing flow. So what is the generative model in machine learning domain? Generative model helps you to generate a lot of synthetic data across different parameter spaces. For example, if we don't have a certain values of parameters for a given kind of maybe a strain data in this case, and we need those kind of values, these generative models can actually, after being trained on certain type of data, can give you a lot of synthetic data, which also needs to be verified based on some of the true data. So this gives me the, this is the architecture of the conditional variational autoencoder. And on the top of this conditional variational autoencoder architecture, I put this planar normalizing flow. The main reason I put a planar normalizing flow on the top of a variational autoencoder because the CCSN data is highly stochastic. In some of the regions, there are a lot of variations. So sometimes this complex data cannot be well captured by this single latent space of the conditional variational autoencoder. I'll be very happy to explain later on if you have questions regarding the structure of each of this. But in a conditional variational autoencoder, what we do is that we give some input data, and this high dimensional input data is compressed by the encoder and then put into a lower dimensional space known as the latent space. Later on, from this latent space, samples are drawn and the decoder reconstructs the input data. For my case, I can have a very simple Gaussian latent space if I use only the conditional variational autoencoder. However, due to the nature of the data that I have, I input another structure or another neural network architecture known as the planar normalizing flow so that it can capture the individual stochasticity or the randomness of the CCSN data. Now, what we do, after we have trained our neural network with the CCSN data, for one particular parameter set, that means a particular value of A, omega, and equation of state, we generate 1,000 waveforms. And after we generate 1,000 waveforms, we take an average of these waveforms, and then we try to compare with the true value. So let's see how this turns out to be. So we need to check our neural network from time to time. So even though this plot looks like some of the microbes or bacteria under the microscope looks like something like that, but this is not such this. So we have a lot of equation of state when we put in the neural network. To make sure that we have a proper training, we need to be assured that these equation of states are grouped together. This plot actually gives me that kind of result. So if you see that all these equation of states, I simply ran out of, I think, my Python code ran out of some legends over here based on the colors, so some of the legends might be repeated. So in this plot, what we are looking into is that for each equation of state, all the waveforms should be clustered together. That means my machine now recognizes or understands the waveforms based on the equation of state. This is a very preliminary check just to make sure that we don't run into any other issues before we try to generate our plots. In other sense, you can say that this is a kind of sanity check for our machine learning model to make sure that the equation of states are grouped together. The individual equation of states are grouped together. And after that, we move to the results of generating the waveforms. So as I showed that in the data section, I have taken a lot of equation of state and with a wide variety of A and omega. However, due to time constraints, I'm only going to show some selected results from here. So from here, you can see that for this particular equation of state A and omega values, I have compared the machine learning generated and the true waveforms. And I have done this for two different kind of equation of state having some particular values of A and omega. So this orange, the blue line shows the true waveforms that comes from the simulation. And the orange line shows the generated waveform. So as you can see that the true waveform and the generated waveform almost overlap each other. This is a kind of visual evidence that we want to see after having some understanding of the clustering of the equation of state. We want to look into the overlapping or to the extent to which the waves would be very close to each other. And I have done a similar result for another equation of state, SFHO and HSDD2. However, you can see that for SFHO in this region is not overlapping completely. That means for this equation of state, there is a certain issue which the machine is not able to learn properly. Hence, we are getting a poor reconstruction. This actually happens. We can, as a machine learning people, I can tell you that we can forcefully make this look good, but that won't have any good effect. So we want to make sure that whatever the result that's coming out has to be without any issues. So especially for this SFHO, I really struggled a lot with SFHO, but still I wanted to show this result as like a limit of the machine learning application is that you can see over this region also we do not have a proper overlapping. So now we find that across some of the equation of state, we do have some overlapping. However, for some equation of state, we do not have a good overlapping. However, this is not the end. So after we find out to what extent the true and the generated waveforms are overlapping, we want to calculate the mean squared error and the MAPE, mean absolute percentage error, between the true and the generated waveform. So as you can see, for this across this equation of state, I have calculated the range of the MSE. So this range comes from, like as I mentioned, that for one equation of state, we have different physical parameters for A and omega, and for each of them, we generated a wide range of waveforms for this particular work, and then we put those true and the generated values, and we calculate the MSEs, and hence we put a range over here. And as you can see, the MSEs are quite pretty low. And on the top of that, we also wanted to check the MAPE because these MSE values are pretty low, but we also wanted to see how much in the terms of percentage error we have between the true and the generated waveforms. And here we have tabulated the values over here across the equation of state. We could have easily done this. Actually, in the original work, we have done this for individual equation of state, and then we put a table where we have A and omega, then we calculate individual MSE and MAPE. However, for the presentation, I wanted to accumulate all of this together and put it in a single result. So with this, I'd like to put my summary. The most important part is that currently the training takes for all these waveforms that I've collected from this richest paper, it takes only 2 hours to train, and the generation takes only a millisecond. Even though I generate 1,000 or 10,000 waveforms, once the machine learning model has learned how the things are working, you can generate even 1 million of waveforms within few seconds for a wide range of physical parameter. And then you can also match with the MSE and the MAPE for individual true and the generated value. And the future work would definitely be, as I mentioned earlier, that I would like to definitely include some of the CCSN models that we have been discussing for the past 2 to 3 days over here. And probably you might receive an email from me requesting for the data access later on. And then this is one of the final goal. Actually, this final goal was triggered when I was talking with Marianne, and she mentioned that what if it's possible or not, we train on a different CCSN model, and then we want another things to be discovered from there. Yeah, so with that, I'll take your questions. Thank you for your attention.
Thank you, Surojit. There is already hands up.
So Matt Edwards' group in New Zealand have a paper that does this using the Richter's waveforms and GANs. And so I wondered if you'd seen their work and if you've compared how your results compare to this.
Well, as you know, sometimes GAN can also be computationally expensive because how to say, it's much better because I'm directly using the strain data. So for me, if I use GAN, it will be just a waste of computational resources. GAN would work very good if I take the image, for example, if I take a spectrogram or something of that sort. Yeah. And the other reason, as I mentioned, that since I also want to know the effect of this stochastic nature of some of the CCSN waveforms, because I remember you also showed some of these waveforms which are very much unpredictable at a certain point of time, have a lot of fluctuations. So if we put the CVAE, the variational autoencoder, and also the planar normalizing flow on the top of that in the latent space, that would be very helpful in catching those posteriors accurately. That's the reason I'm quite motivated to use this technique.
Are there other questions for Surojit? Yes?
It seems like magic. So if I took a model, say a 15 solar mass model, and I run that model at 3D full physics, if I had infinite computer time, I run it, 1 million times. And each time I run it, I introduce some slight perturbations so that the results will differ. This is a stochastic phenomenon, as you said. Do we really expect this to be able to predict any one of those waveforms well?
That's a very good question. So there's something called latent space. Let me just go back to this one. I was really expecting this question, to be honest. So as you can see, this is called latent space. So this latent space for the variational autoencoder is Gaussian. That means the distribution is Gaussian. So whenever I generate one waveform, it will be sampled from that Gaussian distribution. If I generate 1,000 waveforms, those 1,000 different points will have different variations. That means if I generate 1 million waveform, all those million waveforms will have some variations in itself. That actually kinds of like adds up to the stochasticity of the CCSN waveforms as well. But when we show our result, we take an average of those waveforms. But in principle, when I add the planar normalizing flow on, when I add the planar normalizing flow on the, on the top of this on the top of this latent space, I can really catch all those minor variations. This is the one of the aspects that I would like to mention over there. Yeah.
I guess you could test what Anthony is suggesting by excluding some of the waveform from your training sample and put a testing sample in order to check this.
Yeah, that's true. That's what we are currently trying to do, because we want to see if we can do the good prediction across the other progenitor mass, because this data is just related to one progenitor mass, and we want to see if we can do that for others as well. Yeah.
Very nice. I think we should thank Surojit again